everyone. Thanks, Jonathan, for the nice introduction. And by the way, Richard is actually my PhD supervisor's PhD supervisor. So, so privileged to work with Richard. Today I'm going to talk about sort of verification and programming of quantum systems, right? So formal verification has been very successful in classical computing, in hardware and software, and it's routinely used by companies like Microsoft, Intel, NASA, Amazon, and Facebook. So my question was, can we do something similar for quantum computing and quantum cryptography? But you may say, do these things exist now? Do we have quantum computers? General purpose quantum computers could be some years away, right? So these are computers that are capable of breaking RSA and DES encryption and cracking, in the internet. So this could be a number of years away. But in the last 2-3 years, there's a lot of activity from big companies and governments and funding agencies pouring a lot of money, and there is a race for quantum supremacy. So the big players like IBM, Google, and Honeywell are involved in this. And it's seen a lot of activity in the last couple of years, especially during the pandemic, okay? So, and quantum computers actually do exist already. So these are what are called NISQ computers, which is noisy intermediate scale quantum computers. So IBM Q is an example. Here's a picture of IBM Q. And Google has its own quantum computers, and a startup in the US called Rigetti also has a quantum computer. So a number of companies, Honeywell, have their own quantum computers. These are already available. And they work on a very small number of quantum bits, about 50 to 75 these days. And they're, as they're called, noisy intermediate scale quantum computers. They are obviously very noisy, and you'll see a bit later in the talk how noisy they are. And noise correction is required to get actually good results. But they exist, and there are already applications to various fields, such as quantum molecular simulation for discovering new drugs, quantum machine learning, or optimization. For example, Volkswagen has used quantum computers to demonstrate route optimization in buses in Lisbon. So people are using these computers to do actual applications these days. And they tend to be a bit faster, not significantly faster than classical computers. Okay. So a typical architecture is quite similar to a classical computer architecture. So you have a top layer with applications which are programmed in some kind of a high-level language. Typically, it's Python these days. And then these programs are sent over the cloud to a quantum computer where there's a quantum processor, and that will crunch your quantum program and return the results, right? So this is a typical way of doing things, and this is from Rigetti, but IBM, it's the same picture, or the Google is the same picture. And there are dedicated cloud providers like Microsoft and Amazon who are now into this game as well. So they don't actually have quantum computers, but you can go to Amazon and then run your program on someone else's quantum computer, right? So you can do these kind of things. So they are available now. You can run some programs. You and I can run some programs, and they have some applications already. Okay, on the other hand, there is this field of quantum communication and quantum cryptography, which is quite a mature field. It's been around for maybe more than 20 years. And this doesn't really involve computation particularly. It's actually sending secret keys, which are typically encoded in photons over fiber optic cables. And the idea is that if there is an eavesdropper, the eavesdropper will be detected when they try and copy or try and learn something about the keys. So QKD, the quantum key distribution, has been proved to be unconditionally secure. So theoretically, it cannot be broken. But how about implementations? For example, Toshiba manufactures these boxes which can be used to send keys using QKD, but the actual implementation might be, vulnerable to attacks, right? So this theoretical protocol isn't, but the implementation could be. Okay, so then I was part of a EU project which built a network using QKD components across Vienna. This is already about 10, 15 years back. Okay, and in the UK, BT is doing something similar. They built a quantum cryptographic network from their research facility in Adastral Park up to Cambridge, collaborating with various other universities and companies. And this uses quantum key distribution equipment from ID Quantique, which is a Swiss startup. I mean, it's actually a big company now. So, and the thing is, it's done over standard BT fiber optic cables and through BT exchanges. And this thing has existed for a year. So all of these things are now working. And BT has recently announced that they're going to use Toshiba equipment and build a network across London. And China, so not only you can do this with cables, you can do this in free space. So keys can be distributed in free space. And China has launched a satellite even 5 years ago for secure communication using QKD. Okay, so all of these things need to be secure. And if you build quantum computers, they need to work correctly and securely. So that's why we, could be interested in formal verification. And I've been talking to BT over the last 6 months or so, and they're really interested in formal verification and want to have some projects, looking at their network, for example, and components. Okay. So this is the kind of motivation for what I'm doing. And since many of you may not be that familiar with quantum computing, I'll give a sort of a 10-minute introduction to quantum computing. Okay. So so you have classical states 0 and 1, a quantum system or a quantum bit, which is abbreviated qubit, is given by a linear combination of the basis states. So it's a combination of 0 and 1, right? Written as alpha ket 0 plus beta ket 1, okay, where alpha and beta are complex numbers. So all this says is the state is a superposition somewhere, with a combination of 0 or 1 or in between 0 or 1, okay? So if you think about a coin, for example, so you have heads or tails, but if you toss a coin up, there are intermediate states that have part heads, part tails, right? So an example of a quantum state is here, which is square root of 0.3 ket 0 and square root of 0.7 ket 1. So this is a quantum state. Of course, I'm not using complex numbers there, but just to give you an idea, this is a qubit, right? And if you actually square the coefficients, which are called amplitudes, then you get, if you add them up, then you get 1. Okay, so this is a quantum state. So a quantum state in superposition, so you might not generally know the state of this, this system, right? When you have alpha and beta, and you have to make an observation or a measurement. And this actually collapses the quantum state to a classical state, either 0 or to the state 1. So it's like similar to the coin. If you toss it up, you won't know the state when it's spinning, but once you catch it, it comes back to 0 or 1. And again, you must have heard about the Schrodinger's cat, right? Dead or alive, this kind of thing. So as an example, if you measure the state 0.3 ket 0 plus square root of 0.7 ket 1, you get either 0 with probability 0.3 or 1 with probability 0.7, right? And once you measure, it's down to a classical state 0 or 1, right? Okay, so similar to classical gates and circuits, we have quantum gates and quantum circuits. So the Hadamard gate is a very simple gate that takes one quantum bit and places it in a superposition, in an equal superposition. So it takes a 0, that's actually a classical state, but then gives you a superposition of 0 plus 1. It's an equal superposition because if you measure, then you will get 0 with 1/2 probability and 1 with 1/2 probability. Okay, and similarly, it takes 1 and then gives you 0 minus 1, and it's denoted by H here. That's the Hadamard gate. And note that all quantum gates have to be reversible so that it fits in with the mathematics of quantum mechanics. Okay, then there are some gates which are single qubit gates, which are called the Pauli Gates. The first gate is quite similar to a NOT gate, a classical NOT gate. So when you have a quantum state like this, alpha ket 0 plus beta ket 1, what it does is it flips the 0 to a 1 and 1 to a 0, right? So that's like a NOT gate. And the phase shift is actually just takes the a quantum bit and turns the plus sign into a negative sign. And then there is a combination of these two called the Y gate, which actually turns the 0 into a 1, 1 to a 0, and then puts a minus sign in between, okay? And then the fourth gate is the identity, and it does not change the input. So these things actually form a group, and that's why it's called a Pauli gate. It forms the Pauli group, okay? And then you have a 2 qubit gate called the control NOT gate, which acts on 2 qubits, okay? So what it does is if the first qubit, which is called the control qubit, it's 0, then it doesn't do anything to the next qubit. So this is the input, this is the output of the gate. So if the first qubit is 0, the second qubit is not changed. But if the first qubit is 1, then the second qubit is flipped, okay? So the first qubit is the control qubit, and the second qubit is the target qubit, and the target qubit is flipped if the control qubit is set, okay? And this is quite similar to an XOR gate in classical computing, okay? So, so far it's all been fairly straightforward, but unlike classical states, there are 2 qubit states, quantum states, that cannot be decomposed into a combination of 2 single qubit states, right? So if you have 2 classical states, you can turn them into 2 single classical states, but here you can't do that. So for example, the state 0, 0 plus 1, 1 cannot be written as a composite of 2 single qubit states. And this is also quite curious, because if you measure the first qubit, this is the first qubit, if you get a 0, then your second qubit is actually going to be fixed to a 0, right? And again, if you measure the first qubit and you get a 1, your second qubit is going to be 1. And this happens even if the quantum bits are some distance apart, right? I mean, it could be a few kilometers apart, but as soon as you measure the first qubit, the state of the second qubit is actually fixed. Okay, and Einstein had trouble understanding this phenomenon, and he called this a spooky action at a distance, right? So measuring something here could change the state of a qubit somewhere else many kilometers away. Okay, so and this is called entanglement. These states are called entangled states. Okay, and then there's a sort of well-known protocol. I'll briefly go through this, called the Quantum Teleportation Protocol. So what happens, this is nothing to do with quantum security or key distribution, but it's a protocol. You're sending an unknown quantum bit from Alice to Bob, but you don't have a quantum channel in between, right? So if you had a quantum channel, you could just send the qubit from Alice to Bob. But however, they share prior entanglement. So they share a state like this beforehand, where Alice has one of the qubits and Bob has the other. Okay, and then they also have a classical channel for communication. So Alice is sending her qubit to Bob, and then the original qubit is actually destroyed, because if it isn't destroyed, you would be making a copy, and that's not allowed by quantum mechanics. Okay, so I won't be able to go through details of this protocol, but it's a very standard protocol. And then the circuit corresponding to this protocol looks like this, right? So here is the quantum teleportation circuit. And the first part here is what creates entanglement. So Alice has Q0, the qubit Q0, and Bob will receive the qubit in Q2. So Alice has Q0 and Q1, these two lines here. Bob has the third line. Bob will eventually receive the qubit Q0 on line Q2, and this is the circuit, right? And so Q1 and Q2, this shares the entanglement between Alice and Bob. And then Alice does something on her own qubits, and manipulates her own qubits, and then makes measurements. And when she measures, she gets some classical bit values, which she will send to Bob, and Bob will do these gates, X and Z, to recreate the value that Alice originally had. So this is the Hadamard gate, this is the C0 gate, these are measurements, and these are X and Z gates, which we've all seen before, okay? So by this, Alice is kind of teleporting an unknown quantum state to Bob, where she doesn't know what exactly the quantum state is, okay? And so you can write this in terms of a circuit, but you can also, what you can do is you can actually code this up in Python, typically, and run it on an IBM quantum computer. And I didn't really want to risk running it in real time, but I ran this on the IBM quantum computer before, and it says, so this is an actual IBM quantum computer, and you can run it on this, or you can run it on a simulator they have as well. Okay, but this is a run on the actual IBM Q, and I got these results. Okay, so I ran it, or the computer ran it 1,024 times. And so the teleportation was to try and teleport the qubit 0, just the state 0 from Alice to Bob. And the result is unfortunately quite error prone. So if you see the result here, so Bob gets 0 with some kind of 60% probability, and Bob gets 1 with 40% probability. So this is noise in the IBM system. So it's only sending the right quantum bit 60% of the time, okay? And if you actually do use the simulator, you would send it correctly every time, but now the noise makes it quite error prone, okay? So this is an actual quantum computer running a circuit, and later on I could show you how to do that after the talk if you want. So if you didn't realize these things exist, they do, and they're typically programmed using Python, okay? And so I feel Python is not the right language for doing this. So there is my slogan, Python is the Fortran of quantum programming, okay? So what I feel is it's not the right language. This is like when we had Fortran back in those days. People were programming lots of things with Fortran. And so I actually went and Googled Fortran, and it seems quite a lot of physicists are still using Fortran to do their programs. So maybe I should change this to Fortran is the Fortran of quantum programming. But anyway, quite a lot of development takes place in Python. But I feel we could use high-level programming languages, because then you can do type checking, you can reason about program correctness. And with this in mind, I, together with a colleague, Simon Gay, developed something called the communicating quantum processes. This is based on the pi calculus, extending that to the quantum setting. And of course, you see the analogy from communicating sequential processes to communicating quantum processes, although it's based on the pi calculus rather than CSP. And you can do some interesting things like using pi calculus linear types to enforce the no cloning principle of quantum mechanics. Okay, this is already quite old work, which is published in 2005. And similar efforts around that time and later are languages called Quipper, and Microsoft later on has developed their own language, high-level language based on F#, and it's called Q#, but it's not really, doesn't work for distributed computation. So our work is focusing more on concurrent and distributed computation. Okay, and Richard will talk a little bit more about the programming specification side of things. In the time left, I'm going to talk a little bit about verification. Okay, so those of you who are not familiar with formal verification, this is trying to prove correctness of systems. Specification says what a system is supposed to do, and verification is, does the system do what it's intended to do, right? And they're using formal maths or logic and algorithms to prove whether this thing works, right? So your system meets the specification. So this is formal verification. And there are quite a lot of classic examples where software or hardware failed, and you must have come across these examples. Ariane 5, the rocket failed and crashed because, for example, one of the problems was software failure due to a 64-bit floating point number was assigned to a 16-bit signed integer, and this had an overflow and raised an exception, and this wasn't caught, okay? So then there's the failure of Patriot missiles. This also was software error, and 28 people lost their lives, and various other examples in software. But also I want to highlight the Pentium bug, floating point bug, and a mistake in the floating point division led to incorrect errors. And this cost Intel about $475 million. Okay, so and as Dijkstra said, program testing can be used to show the presence of bugs, but not their absence. So that's why you need formal verification. And it's now routinely used in hardware and software. And in fact, Richard told me to point out a lot of hardware companies are using this because hardware is kind of easier to verify compared to software, and most of the hardware companies now use formal verification to validate their designs before shipping. Okay. Okay, and it's also been used in building a verified compiler for much of the C language. The Paris Metro line employed a formal verification method called the B method, in order to automate processes. And so, like I said, it's routinely now used in the classical setting by large companies. Okay. So there are different techniques in formal verification. I just want to point out 3 different ones here. Model checking, which I'll talk about a bit more, theorem proving and equivalence checking. These are different kinds of methods. The model checking and equivalence checking are typically more automated. Theorem proving requires some kind of expert manual intervention. So model checking is a method of automated verification. If you have a model that is expressed in a suitable modeling language, it can be transformed into some kind of state machine or an automaton. And you can check the model against a property or a logical formula and see if that logical formula is satisfied by the model. Okay, so you can do this automatically quite easily these days. And if it doesn't satisfy the formula, you can actually produce a counterexample and show why this hasn't satisfied it. So Gavin Lowe famously used a model checker to detect a subtle security flaw in the Nathan and Schroeder public key protocol. Although the protocol had been used for many, many years, people hadn't realized there was a security flaw, and Gavin Lowe used a model checker to find the flaw and fix it. So these days, security protocols are verified using model checking. So I thought quantum protocols for quantum key distribution, random number generation, various other things are ideal targets for verification. right? And possibly you could detect some subtle flaws people haven't found from testing these things. And of course, like I said, there are commercial QKD systems built by Toshiba, various other people, and also things that are installed into networks like BT. So we need tools for validating these implementation. And a lot of these protocols are have some, the QKD protocol has some classical pre and post processing procedures. So you need to verify some classical things, and also they are included in classical hardware and interface components. So you could also verify this combination of quantum and classical things. Okay. So we started looking at model checking of quantum protocols, but there are several issues you need to consider. The state space of a single qubit is infinite because, as I showed you, the coefficients are complex numbers. So you could have any complex number as a coefficient. So a single qubit itself is infinite. And the state space, when you start combining qubit quantum systems, then it grows exponentially. And there are infinitely many possible quantum operators. So these are bad things for us because model checking is state-based, and there's a lot of explosion already with classical systems. So we need to tackle these kind of things, and quantum measurement is probabilistic. So you need to take into account that as well. Okay, so initially we tried using a probabilistic model checker, which is the PRISM model checker which is from the University of Birmingham and now Oxford. So we tried to use the model checker to analyze the BB84 quantum key distribution protocol. So using that, we could compute the probability of detecting an eavesdropper when certain number of qubits are transmitted, and the probability that the eavesdropper obtains certain number of transmitted bit values, can he or she learn something about the key. So these kind of things we can do, and we have a publication doing this, right? But then we realized probabilistic model checker isn't enough because there are strange things like superposition and entanglement we want to capture directly. So we started building a tool called QMC. It has a type concurrent language for quantum protocols, and then it has a simulator. For a restricted set, it's called Clifford operators. It doesn't do the whole quantum space because then it won't run efficiently. And it uses the logic called QCTL, which is a quantum computation tree logic. Okay. So the idea is you model a quantum protocol using this modeling language, and then you describe a property like desirable or undesirable behavior in this logic QCTL, and then you can run the model checker to automatically verify if the property holds for your specification. Okay, and the logic is, if you know CTL, computation tree logic is used in classical model checking. This is just an extension of CTL. But CTL allows us to reason about properties of quantum state. For example, we can check whether two states are entangled or not. Okay, so these are the kind of things we can check. So I proposed the application of formal verification many years ago, about 19 years ago, in a very short paper. And I believed even at that time we should start looking at it. And we've been steadily working on various techniques since that time, since our purple paper in 2005. And then we have this model checker. And then we developed some equivalence checking later on to show that to check whether two quantum systems are equivalent or not. So those use slightly different techniques. And then we did some theorem proving using some proof assistance to check properties of quantum cryptographic protocols. And then more recently, Richard has actually implemented our quantum process calculus CQP, and he'll give you a demo and talk about that a little bit more. So the idea going back is, instead of something like Python, we want something higher level and more concurrent distributed to deal with protocols and to have types and to have type checking. And Richard will give you more details. And that's kind of more recent work that mainly Richard has developed. And even more recently, we have started looking at some property-based testing of quantum protocols, in particular Microsoft's Q# language. So this is quite a lot of work over the last 15 years or so that you can have a look at. Already exists, and there are software tools now available, a quantum model checker, equivalence checker, and Richard's Qt, which is available on GitHub. And we also have this testing framework that's available for people who are interested in. Okay. So recently, so this is all theoretical work, mostly with some tools which are prototypes, but we've been talking, like I mentioned, to BT recently, and other companies are also kind of interested in using some of these techniques. So hopefully in the next 4 or 5 years, we could apply some of these techniques to actual quantum systems, quantum computing, quantum cryptographic systems. And it's not just my work, there's been quite a lot of other people working on these things as well. So I think the basic frameworks are still, are there now, and now we could try and apply it to real systems. Okay. So I'll stop here. I think even a bit earlier than Richard was predicting, but I'll stop here and give, let's say, 5 minutes for people to ask questions on this part. And of course, you can ask me later as well. But if you want me to clarify something, we have 3 or 4 minutes, and you can unmute yourself and ask me questions.
Does anyone have any questions now, or would you rather wait till the end? If you do have a question, just unmute yourself. Well, one thing I'll say, since we're breaking briefly now, is that, yes, I have another actual real event after this. So Keith Lines has very kindly agreed to take over the questions right at the end. So I'm sorry I won't be there for that, but I'm hoping to hear the rest of the talk at least.
Perhaps I should add that if anyone wants to put their questions in the chat, I will keep an eye on that and raise them as necessary. So if you want to do that, that's also a possibility.
Can we use chat for questions? Because sometimes you think of something while they're giving the talks going on. Sometimes helpful to write it down straight away.
Yeah,
that's fine. Yes, go ahead.
Yeah, chat is fine. Or sometimes people are shy to ask. You can put it on chat. Yeah, feel free for a couple of minutes. I'll wait. If anybody has some questions on this part, we can discuss. Otherwise, Richard can start.
Just a quick silly question. What about declarative languages? Are they no good for?
No, I mean, there are people working on declarative languages. One of the earlier programming language was using declarative languages. Of course, you can use declarative languages, right? And I can't remember what the name of these things were, but then you could have horse-style assertions to actually check things. People have done that as well. So yes, of course.
So as far as you know, they're equally as good or as bad.
Yeah,
I think that's a mistake, actually.
Sorry?
Quantum mechanics is very weird. It is ordered. It is not in parallel. Things happen in order, and that is fundamental to quantum mechanics. That's part of this spooky action at a distance paradox. And declarative languages, I'm afraid, might not hack it.
And also the other thing is entanglement for some, could be a sort of a global thing, right? And you have to deal with that. So it's not a local property particularly, right? So I think that could also lead to some difficulties, right? So yeah, but people have worked on it, so it's not certainly infeasible, I would say. So any other questions?
Yeah.
So if not, I'll hand it over to Richard, who will talk a little bit more about Qt. Thanks for listening, and I'm available later on for chat. And also, if you want to see something running on the IBM Q on the actual computer, I can show you that too. I just didn't want to risk it during my talk and have it fail or something. Yeah. But okay, thank you very much, and over to you now, Richard.
Right, thank you, Raja. Over to Richard.
Okay, I will start sharing my screen and go to full screen, I think. So, you can hear me, Jonathan?
Yes, all
Right.
fine, and the
Good.
screen looks fine.
Okay, right. So Raja and Simon Gay produced a definition of a programming language, which got into POPL, communicating quantum processes, and it is a programming language, but it's a theoretical programming language. It didn't have an implementation. Indeed, I think it wasn't implementable. Riefel and Pollack was a paper that Raja pointed to me. To my shame, pointed me to, sorry. To my shame, I'm not a quantum physicist. And it explains quantum calculation and got rid of some of my fears of quantum computing. And I found those calculations in Riefel and Pollack, even though they're very small examples, I find them quite difficult to do in pencil and paper. So I resolved to use a symbolic quantum calculator. And I just realized that I could implement CQP with a symbolic quantum calculator. And that's what Qt is. It's available on GitHub with lots of examples and documentation. It can do BB84 QKD, and I'll come to that later on, and even do some proper quantum computing examples as well as protocols. There's lots of things I could talk about, but in the short time I've got available, I can't do them all. So Raja's dealt with some of the quantum stuff. I'll talk about the language, briefly mention the symbolic calculator, probabilistic execution, and the resource accounting for qubits, which Raja introduced under the name of linear typing. And then I've made some more changes to the language, which are all crossed out here because I haven't got time to talk about them. So, if you look at a description of a protocol on in a description of a protocol about quantum stuff, you can find what protocol agents can do. So they can obtain a qubit. You can get a qubit, maybe you can get a qubit in a particular state, one of the standard states, 1, 0, plus, minus. You can put a qubit or some qubits through a quantum gate. And although Raja said there's an infinite collection of quantum gates, there's rather few of them that get used in quantum computation. H, I, X, Z, and C0, and the Pauli Gate. Not very many. And you can measure a qubit. Or as I've just realized, you can measure 2 qubits at the same time, but I haven't put that into the language yet. You can send or receive a qubit to another agent. That's very important. And you can also send or receive classical values, such as lists of numbers or lists of bits. And you can do some classical calculation. And that's about all you can do. So those ought to be the components of a language which is describing protocols. All of these things should be steps in protocols. So Raja and Simon based their language on Milner's pi calculus, which is a very stark language designed to examine how process execution could work, what the semantics of process, semantics of concurrent processes could be. And that starkness makes it possible to do certain sorts of things, in particular, checking that you're not cheating with quantum qubits. So a process definition is a process name, some parameter names, and a process description. And a process description is an IO step followed by dot, followed by a process, or it's a Q step followed by dot, followed by a process, or it's a binder, possibly followed by dot, followed by a process. Or it's a process invocation, given a process name and some arguments, or it's a parallel process, parallel composition of several processes, or it's an alternate, guarded alternate of several processes, or it's a condition executing one or more, executing one of several processes, or because for boring syntactic reasons, I had to have a representation of the null process. And apart from the Q step part of that, Milner would recognize all of that. None of that is novel in the pi calculus, except for Q steps, quantum steps. So IO steps are sends and receives. Bang means send. You give a channel expression, bang, and then a tuple of values you're sending down that channel. Robin was very keen on tuples. They're all over SML. Or you can receive a tuple of values down a channel, from a channel, and you bind them to names, and then you carry on with what follows the IO step. And a quantum step, well, there only are two really. You can put one or more qubits through a gate, or you can measure one qubit. The result of that is you get a bit which you bind to the name X. And a binder, well, nu creates channels, nu q creates qubits, and because it's very convenient, there's also an initialized form of nu q, where you can specify which qubit you want. The value you give in E is a classical value, but it'll be a vector of some sort. Or you can, I couldn't resist putting a lets in. Robin would get very cross at this point, but you can take a classical value, E, and expression E, you can compute it and you can bind it to the values in a pattern. And a parallel process is just a bunch of processes separated by vertical bars. An alternate is guarded alternate. It's an IO step followed by a process, or it's another IO step followed by a process, or it's another IO step followed by a process. And one of these IO steps succeed and the others don't, and you choose the process followed by the succeeding the successful IO step. A conditional is just if then else, or I added match. Now all the capital letters in this description are expressions. All the single letters are, all the lowercase letters are names. In the pi calculus, communication channels can be sent and received in messages. That's how you configure a collection of processes, and that's what Robin was very interested in when he designed it. Nowadays, in QtPi, so can qubits. And you can also send classical values. That was long, QtPi, process calculus was long ago extended to deal with classical values being sent down messages, sent down channels. QtPi is strongly typed. There's a type checker for it. Explicit typing is optional, but I haven't described it here in this example, in this description. A lot of the things that happen in the protocol are calculations. So in the QKD protocol, you calculate the things to do with the bits that you've measured. There's a functional notation for calculation in Qt, which looks a bit like Miranda, but Margaret, it's not lazy, it's eager. I chickened out of lazy evaluation because the protocol, the process language, the protocol part is so eager. It is one thing after another. And to deal with Qt accounting, I had to put some restrictions on the language. One of the restrictions on qubits is in physical reality, there is absolutely no way, there's a theorem about this, there's absolutely no way you can duplicate a qubit. You can measure it, but in so doing, you destroy it, or you destroy the state it was in. You cannot start with a qubit in some unknown state, do some calculations, and finish up with 2 qubits in the same state. It's impossible. Even in a teleportation example, you destroy 1 qubit when you're creating a state of another. So to simplicity, I struggled for a long time with the restrictions you needed in the functional language. But in the end, I settled for the draconian restriction that functions can't have anything to do with qubits. They can only deal with classical values. Well, I built a symbolic calculator because I wanted to do some calculations using variables. Riefel and Pollack had some. So A's and B's, which stand for unknown quantities. You can't do that if all you're dealing with is numbers. And also I was scared of approximations because you often use 1 over the square root of 2 in your calculations. And the real number approximation for 1 over the square root of 2, when you square it, is not exactly 0.5. So I use a symbolic calculator with a few constants, and you can have variables in this as well. The semantics of CQP were that when you got to a measurement, which is probabilistic, you went both ways. You created 2 branches in the calculation, labeled with the probability of measuring 0 and the probability of measuring 1. That's no way to write a simulator. Qt actually throws a random coin and throws a fair coin in at random and chooses one way or the other. Not always the most likely. So when you run a Qt program, that's one reason, and there are others, why you don't always get the same execution. And I was quite keen to turn my experience with concurrent languages from the 70s into real life. So there's lots of stuff in Qt, which means that it doesn't do things which are indefinitely unfair. It's not necessarily fair, but it's not indefinitely unfair. And the reason I got into designing a programming language or implementing a programming language was because I wanted to check this no sharing, no cloning. When you send a qubit is not like a classical bit. A classical bit is a value. You can assign a bit from one variable to another and nobody cares. A qubit is a great big physical thing. And you can send a qubit from one process to another, but when you do that, you haven't got it anymore. So you have to be sure that qubits which are sent away, even though they're in scope in terms of the language, can't be used again. And there's also a no sharing notion. If you split into a number of parallel processes, you can't share the same qubit between several parallel processes. It has to be in one or another or another. It can't be in all of them. And you have to make sure in your language that there's nothing equivalent to assignment. That's quite easy. But Robin was so keen on tuples, and tuples are really nasty things. If you have a tuple of arguments and you put the same qubit in the argument list twice, you've duplicated it. If you have a tuple of values in a message, you've duplicated it. So you have to stop all that sort of thing going on. I did that using the resource accounting stuff I learned in separation logic. So now I'm going to do some demos, including one which surprised Raja. I'm going to do the Teleportation Protocol. So here is some stuff, which is the basic Teleportation Protocol and a worksheet to run it. Oh, come on, Shift to select multiple windows. I'm using Shift. God damn you. Control Shift. Nope, it won't do. Okay, I can't do that. Right. Here, I hope, I don't think so. Here, I hope, is the coding for the basic teleport program. Window is right. It's taken from the paper, at least at the top, and it consists of 3 processes: a system process, an Alice process, and a Bob process. Roger showed you a circuit for this, but circuits are pretty impenetrable. The system process creates a qubit, acquires a qubit X, which is in the plus state, and a qubit Y, which is in the 0 state, and it entangles them through the C0 gate. And then it creates a new channel, which is capable of carrying a pair of classical bits. And it creates a new process, Alice, giving it the X qubit in the channel, and a new process, Bob, giving it the Y qubit in the channel. And Alice does exactly what Bennett, Brassard, and et al. Said she should do. She creates a new qubit. In this bit of text, she creates a plus qubit. She puts her qubit and the qubit she's been given through the C0 gate. She puts her qubit through the H gate. Then she measures those 2 qubits, Z and X, and she sends the tuple of values she's just actually measured down the C channel. Bob has been patiently waiting on the C channel, received 2 bits, and depending on what those bits are, he puts the qubits, his own qubit, through I, X, Z, or Z times X. Raja wrongly told you that was Y, it's not. Here, I shall now show you here's a window which will run that program. So QtPy, run QtPy over that example. It runs it, and no, not to anybody's surprise, it says initially Alice's Z is H0 plus H1. H is QtPy speak for 1 over the square root of 2. Finally, Bob's Y is exactly the same thing. If I say minus trace, I can show you the horrible calculations that give you that result. So I'm not actually cheating here. It's actually going through all the steps. And Bob is actually, in fact, not having to do anything at all to make that happen. He puts it through the, oh yes, he has, he's put it through the ZX gate, a combination of Z and X to change the sign and switch them around. It's actually working. Now that was a tiny bit of quantum weirdness. I'm now going to, Roger and I agreed I was going to do one thing. I'm actually going to do something else. I'm going to show you the BB84 protocol because I can. Alice and Bob communicate using 2 channels, a quantum channel and a classical channel. The aim of the protocol, and it works, is to generate a one-time code without transmitting it. One-time codes are the pinnacle of the cryptographic world. They can't be cracked because you only use them once. Let's say Alice chooses 1,000 bits. She encodes them as 1,000 qubits, randomly choosing either diagonal encoding, that is plus or minus, like that, that's plus, that's minus, or normal encoding, that's 0, that's 1. And she sends them down the quantum channel to Bob. She records, of course, which she chose, whether diagonal or normal. Bob then measures them. He also randomly chooses diagonal or normal to measure them in. And it's a 50-50 chance that he guesses the same as Alice on each one. Then they compare notes via a classical channel about their random choices. They don't say anything about the bits they've read, just the choices. Now, because Bob has chosen the same as Alice about 50% of the time, provided Eve is not interfering, he will see the same bits that Alice sent. He measured the bits that Alice sent about half the time. So they've got about 500 bits, which are secret. No one else has ever seen them. But Eve might have interfered. So Bob sends Eve classically a random sample of n of his bits. They've arranged beforehand what the n should be. And there's only 3/4 to the power n chance that Eve has meddled with those bits. And if she's meddled with those bits, Bob wouldn't necessarily seem the same as Alice. And Bob will see the same as Alice. So 3/4 to the n, if n is big, say if n's 100, 3/4 to the n, something like 10 to the minus 13. So quantum-wise, Eve cannot interfere without making some difference to what Bob reads. Statistically, Bob and Alice can agree n to be large enough that they probably will spot it if Eve tries to do that. But if Eve hasn't interfered, if those bits agree, they've got a 500 minus n secret one-time code that's never been seen by anyone else ever. Those bits have not been up and down the quantum channel. So all that Alice does is XORs the message with some of those bits and sends it classically down the channel. Bob XORs it with the same bits and the message is revealed to him. Eve cannot get it. It's all done on that 3/4 to the n. So now I'm going to show you Qt running that. Start share screen. Okay, so this is Alice and Bob communicating with each other. This is the standard control file I shall use. Whoops. 100 bits in a message, 20 bits in a hash key, explain that in a minute. 40 bits, the minimum check bits, you'll see that they use many more than that. 10 sigmas to make sure they don't run out of bits to do their calculations, and 1,000 trials. Here goes. This is Alice communicating with Bob, being simulated on my machine. And it happened in 5 seconds, computing. And you'll notice that to send a 100-bit message with all that precaution, Alice had to use 1,313 qubits. And heaven knows how much stuff has been communicated up the channel, up the side. But Alice has, there was nobody interfering, so not to be surprised, nobody got interfered with. So here's the same thing, exactly the same code for Alice and Bob, but Eve is going to get in the way and try and read those qubits. So will Eve be detected? And the answer is yes. She gets detected every time. You can notice up the right-hand side that there are something over 150 qubits being used to 150 bits being used to check the interference, and Eve is detected. It says here, Eve won 0 times, Alice won 1,000 times. But you probably didn't notice when Raja showed you that picture of BT's QKD network. It's a relay network. It's a point-to-point network with relays. Alice sends to Bob on the first step. Bob decodes the message and then recodes it on the next step, creates a new one-time code and sends it to the new Bob, who decodes it, creates a new one-time code and sends it to the next Bob, and so on. The code is, the message is decoded at every step. If you put an extra relay in that sequence, nobody could tell. Alice and Bob cannot tell if Eve is able to spoof messages on the classical channel. Those messages are protected by a Wegman-Carter algorithm and some secret one-time hash keys which Alice and Bob have got. actually what they've got is they've got the first time hash keys and they regenerate it every time. But if Eve is in possession of those first time hash keys, let's see what happens. This is the same code for Alice, the same code for Bob, but instead of a naive Eve, it's got a clever Eve who knows those first codes. And she will win every time. And that's how it's supposed to work, because it's a point-to-point protocol. Alice is talking to Eve. Eve is pretending to be Bob for her Alice. Eve is talking to Bob. Eve is pretending to Alice to Alice to Bob. Neither of them can tell it's happening. Now, I don't know if that's physically possible on the BT network, but you never know. Criminals are very clever. But then again, they've thought of this, so maybe criminals are not that clever. So that's me finished. I'm going to stop sharing, and Roger's looking cross. There we are, 7:05, spot on. Thank you, Keith.
Wonderful, thank you very much. So we'll start with questions in a moment. One thing we could ask you, please, Richard, that wonderful demonstration you gave us with the plastic before we started recording, would you mind giving that us again so we have a record of it? That would be great. Put a bit of time.
Okay.
That would be good. Anyone else, any questions, or shall I take co-chair's privilege and ask the first one? I suppose that everything you've just demonstrated there, that's up on GitHub. So if we wanted to download that for ourselves and have an experiment, then we're free to do so. Yes.
Yes, it's all up on GitHub, but it will all work exactly like that. This is the latest version I'm running here, and it runs on Macs and PCs and God knows what else.
But it could run on a standard sort of laptop.
Yes. This is a Mac Mini, but it runs on my 8-year-old laptop quite happily.
Wonderful. I suppose one thing I'm thinking is looking at the your work with Qt, is it the reason that you looked towards Milner's work rather than Hoare's as the basis for what you did? Were there any particular reasons for that?
You'd have to ask Roger that, because it's his language.
Okay, sorry, Roger, that was a question for yourself. I beg your pardon.
Yeah, I mean, no particular reason, I would say, right? I mean, I think we could have easily used CSP as a basis as well, right? And I think in some ways, some other people have used the CCS as a basis, kind of value passing CCS, and maybe that's in some ways simpler. So no particular reason, right? I think all of these are good candidates. And I think maybe something like CCS would be quite simple. CSP would be simpler. I mean, the pi calculus, because you could pass channels around, right? I mean, so I don't think that's particularly, interesting from the quantum point of view, but so I think you could have used any of them.
It was just a framework, a basis, and that any sort of process calculus, reasonably sophisticated one would have done the job.
Yeah.
Correct.
Okay, thank you. Does anyone else have any questions? Please either pop them in the chat or feel free to unmute yourself. I'll tell you what, I'll ask another one by the way. But presumably it's the next stage in your work. Are you really looking at case studies and ways of application? This is because it's getting on for 20 years now. You say that you've been in this area.
Yeah. I mean, also for 20 years, I mean, it's mainly me and Simon Gay and some students and Richard, right? So I think now with the last couple of years, big companies are involved. And as I said, I'm talking to BT about case studies and also even to NPL, your own organization, right? And there are various startups in the UK with small quantum computers or small quantum random number generators. We are also talking to them. So that's my hope in the next few years would be try to apply them to case studies.
Yes, I don't want to do all the talking here, and if others wish to ask, but while we're here, I mean, how
Margaret's
much?
ready to ask a question. Margaret,
please do. Sorry, Margaret, jump in, ask a question.
You have to unmute yourself, Margaret.
Sorry, no, I don't want to ask a question. No.
Sorry.
Sorry, I don't quite know how that indicated. Why? I was typing something on my email. I had problems getting in. I won't talk about that. Too awful.
Yeah.
Numerous passwords were requested and they're not recognized.
Okay.
But anyway, so I was then replying to a couple of people who kindly made suggestions as to how I could get in. And eventually, Safari had given up then. It just gave up. And so I had to transfer to Firefox and eventually got in via Firefox.
Yeah,
that's normal computing, though, not hard stuff like quantum.
One day we'll all be on quantum computers, you never know.
Well, I've used Zoom almost twice, 2 or 3 times a week. No problem.
No, I think the message from Eventbrite might have been a little bit confusing. I think it said something like you needed to log into your Eventbrite account. And I think that's not necessary because they also gave you the Zoom link, right? And I think
I never saw that. I never saw.
Yeah, because I think you could have just directly used the Zoom link. So I think
probably didn't see that.
I don't know how many.
Sorry about that.
I don't know how many other people fell victim to this.
It's all wonderful stuff, really, isn't it? So, could I ask you, please, Roger? Again, please, other people type in questions if you're interested, or unmute yourself. Please do so. But how much of a field do you think there is out there, and interest and an appreciation for the just sheer importance of this theory? For example, how much better a language with a formal semantics is, how much more sound, how much better the software you will write as a result of this. How much of a field do you think there is out there for that, an understanding of that?
Yeah, I think there isn't a whole lot because the actual people who are implementing, developing quantum systems are typically physicists, right? Yeah. And they don't know a lot about formal verification, formal semantics, these kind of things. So we've had to kind of convince them that this is useful. But I think with companies doing this, like Amazon or Microsoft, Microsoft has quite a lot of formal verification people, right? And Amazon also does. But I'm not sure they're talking to each other, like the formal verification people and the quantum computing people in these companies are talking to each other, right? So I think that's something I'm trying to do to get them to talk to each other. BT somehow has been quite lucky because their optics people are seemingly talking to their software testing and these kind of people. So that's been quite easy. But I think, yes, it's not been that easy, but hopefully over the years we could do that, right?
Yes, it's just so important, isn't it?
Yeah.
We've had a question, well, yes, key, isn't it? Right, we've just had a question come through from Marco. It's for either yourself or Richard. With quantum computers predicted to get large fairly quickly, IBM are aiming for 1,000+ qubits by 2023. Do you think that quantum verification will work around the classical will need some generalization or a way to work around the classical representation explosion?
Yeah, I think my answer would be both, right? I think verification will need some generalization, and we have done some work, other people have done some work on generalizing stuff. And also we haven't done a lot of work using the kind of compact representation in classical verification. We haven't kind of done a lot of optimization, let's say, coming from the classical model checking, for example. So I think we need to do more of those things when we start addressing, certainly, like you say, anything like 1,000 qubits, right? Yeah.
I would add to that. First of all, a joke. Amazingly, Qt could deal with one example which deals with 1,000 qubits, but that's because it's a very peculiar example. But in general, no, the things like Qt will not do 1,000 qubits. Never. I mean, the exponential will get you. But of course, verification is nothing to do with the number of qubits. It's to do with the mathematics of the problem. I think in the case of protocols, which is what we're likely to be working on in the next few years if we manage to get any industrial traction, is the stuff there is the issue there is actually going to be ordinary verification of the control programs, because the code for the Alice I showed you, 2 lines in it, or a little bit more than that, 4 lines in it, are to do with the quantum stuff, and 100 lines are to do with the classical stuff. And that's the same in, that'll be the same for BT. The quantum stuff will possibly have some problems. There have been some hardware bugs already shown in a quantum implementation of BP84. Someone discovered that if you flood one of the detectors with light, you can force it to read a 0 or a 1. So the notion that it reads the stuff that's sent isn't true. But that's a hardware problem. There isn't any, and there are only 2, believe it or not, that I know of. There are only 2 QKD algorithms: the BP84, which is the one that everybody uses, and the Eckert one, which requires a little bit more fancy hardware. You have to be able to switch the hardware through fixed numbers of degrees and things, and that gets a bit complicated. So I think so far as the quantum stuff is concerned, that's not going to be an issue. The issue is going to be, if it's anything, to deal with the fact that are people doing the right thing with the classical stuff? Have they implemented the Wegman-Carter classical channel properly? Have they done the privacy amplification properly? Have they not left the code in memory where some nasty bit hammer stuff can get it out, and so on?
But I think, Richard, your points are good, but I think, like you yourself said, they apply to protocols, right? I think if with quantum computers, you could have quite sophisticated algorithms which require a lot of quantum manipulation. I mean, even Shor's algorithm is quite quantum, right? And
very quantum.
Yeah, so that things could be quite different there, I think, but
yes, but they tend to be, their correctness tends to be established by the mathematics of quantum mechanics rather than by verification. I think it's the control stuff that we're going to have an implementation. It's the control stuff where people might go wrong.
Mm-hmm.
A couple of questions. Sorry.
Yeah, go for it.
Sorry, Margaret here. First of all, would Eve know she was being detected? And the follow-up, is there a test Eve could do to detect whether she was find out whether she was being detected? Sorry.
She can't tell whether she's being detected. All she's doing is receiving qubits down a channel and squirting out qubits down a channel and watching some classical messages. That's all she's doing. And she can't tell whether they've caught her or not. I suppose she could tell if they went quiet. She might decide to pack her bags and run at that point.
Yeah, they could go quiet, right? I mean, that's how this works, right? If an eavesdropper is detected, they'll stop sending the keys and send it via a different channel or something. So she might eventually know in that way, right? Like as Richard says, if nothing is being sent further.
But if you're a policeman, you tell them to keep on transmitting while we get out there on our motorbike.
I'll tell you what, while we wait for some more questions from come through, would you like to give us that demonstration, Richard? That would be very good if you could, please.
So I'm ashamed to say I don't know by what name this experiment is known. I bought some Polaroid plastic on eBay.
It's known as Richard's experiment.
It's not. It's famous. I got it out of the refill and Pollack paper, but it's a famous experiment, right? When I was a sixth former 60 years ago, doing A-level physics, they told me that this stuff, Polaroid plastic, is filter. That's why you have it in sunglasses, so it filters out the polarized light that's reflected from wet pavements and so on, so you don't get the glare. And if you have Polaroid sunglasses, they filter out the glare. They filter out certain Polaroid light in certain directions. And as a consequence of that, they told me that if you take a piece of plastic, 2 bits of Polaroid plastic, and you put them at right angles, and I've cut these this shape so I know which is the right angle, right? The first one filters out all the light which is going like that, and the second one filters out all the light which is going like that, and nothing gets through. So you should be able to see. You should be able to not see me through that piece of plastic there, right? And if I put another piece of plastic in the way before or after the square bit, it doesn't make any difference. It's still black. And this was used at one time for showing people 3D films. Nowadays they use something slightly different. They use plastic which detects circular polarization. This detects plane polarization. But that's not actually what it does.
This is
Roger, we can hear you. Mute yourself.
Yeah.
If you take a piece of another piece of Polaroid plastic, and I ran out of Polaroid at this point, so this one's cut a bit thin, and you put it diagonally across, you can see that light does get through. You should be able to see. Can you see me through the gap? Can you see me through the, yeah, you can see me vaguely through the gap. That's good. I can see you brightly through the gap. If I put my right angle piece, I've got my big piece, got my big piece, and then my little piece, and then my right angle piece. And you will see that light is getting through the middle.
Yes.
And that's because what this plastic does is it does not filter. It does quantum measurement. The photons which are hitting this bit of plastic are oriented, polarized randomly in all directions. And this bit of plastic measures them. Let's say it measures them in this direction. And about half of the photons, when you measure them, will say, yes, I'm in that direction. About half of them will say, no, I'm in that direction. The ones that are in that direction get absorbed. The ones in this direction go through. So about half of them go through. And when I put the second bit of plastic at right angles, this measures them in this direction, and none of the photons, which are like that, will get through this one. But I should say, quantum measurements destroys the state of a photon and forces it to be in the measurement direction it was measured in. That is a completely weird thing about quantum measurement. Now, if I put a diagonal piece on, the first bit of plastic says measure in this direction. This one says measure in this direction. Now, a photon which is in this direction has about 50% chance of being measured that way and 50% chance of being measured that way. So about half the light will get through the first piece of plastic and then the second piece of plastic. And if I put another one, rotating at another 45 degrees, about a half the light will get through that. And you will get, or you should get, something like, what's gone on? Have I done it right? Yes, I've done it right. You get transmission of about 1/8 of the light gets through. And that's quantum measurement in a piece of plastic right before your eyes. You don't need a quantum computer. You don't need a fancy pop. You don't need a fancy bit of physics. You don't need a physicist. All you need to do is write to people on eBay and say, "Let me get polarized plastic."
You don't need millions of pounds worth of hardware.
That's it.
I think, is there any other comments? I know we've had a couple from Tom. Anybody wants to comment or add anything? And then I'll...
There are a few questions on chat, right?
Yeah.
Oh, Tom Lake says, I would suggest this is just the wave process, nothing quite about it. Absolutely not. The wave process does not explain it at all. It is doing quantum measurement, and it is because quantum measurement is weird. Quantum measurement cannot explain the 45-degree effect.
Okay, and we've got another question here from Mark. If you can see that, shall I read it out? Do you think enough funding effort is being put into researching quantum verification? Will developments in quantum software hardware outpace verification of these tools?
Yeah, I think not enough funding is being put into verification. A lot more funding goes into software, hardware, and that's certainly happening. But we are talking to research councils, we are talking to companies, so maybe some more funding will go in the next few years, but certainly not enough is being done.
Well, I suppose it comes back to the point we were discussing earlier, that there just isn't the appreciation of just how important these subjects are within within software and coding generally. It always has been. It's been there right from the scratch, right from
Yeah.
from the start of these subjects.
Yeah, and you know, some high-profile thing needs to fail before people will start looking at these things, right?
Yeah.
I mean, that's what's happened with classical computing. Something needs to blow up before they will spend money on.
Yeah.
So hopefully not, but
Software quality is what it's all about, isn't it? Good.
Yeah.
Well, the little bit of formal reasoning we can do in Qt to say that you can't cheat with the qubits would be helpful. It's not in Python. It won't be in Python. It's certainly not in Q#, which is not based on F#, unfortunately. It's based on C#, which is, of course, a version of C++. So Microsoft is programming quantum computers in C++. Heaven preserve us.